So how did we come up with our current model of the atom? In 500 BC, a clever Greek man named Democritus thought that stuff might be made of tiny solid balls called atoms. 2,300 years later, another man called John Dalton thought that each element might have its own atom. But in 1897, J.J. Thomson made an incredible discovery. He built an electron gun, and he realised that atoms could give off smaller particles called electrons. So, atoms weren't solid after all. Thomson called this the plum pudding model of the atom due to its uncanny resemblance to a plum pudding. The electrons were likened to the plums, and the ball of positive charge holding the electrons in place is the pudding. But 12 years later, Ernest Rutherford proved this model wrong in his famous alpha scattering experiment. He fired positive alpha particles at a thin sheet of gold atoms to see how much the alpha particles were deflected or scattered. Now, if the plum pudding model was correct, the alpha particles would simply pass through the gold atoms. But surprisingly, 1 in 20,000 alpha particles were deflected backwards. So Rutherford deduced 3 things about the atom. Firstly, the nucleus must be very, very heavy, because if it wasn't, the alpha particle would knock away the nucleus like a snooker ball. Secondly, the nucleus must be positive because it deflected positive alpha particles. And thirdly, it must be very small because most of the alpha particles missed it completely. Rutherford called this the nuclear model, with electrons orbiting the nucleus like planets orbiting the sun. But there was a problem with this model. In the same way that a coin loses energy as it spirals toward the centre of a coin funnel, the orbiting electrons would quickly lose electromagnetic energy and would spiral toward the nucleus. In the nuclear model, atoms would collapse. Now clearly this doesn't happen, so in 1913, Niels Bohr came up with a solution. He imagined that electrons filled up an atom in shells, or energy levels. You could think of it like books filling up a bookshelf, and once an energy level is full, the electrons can't go any lower, and this prevents the atoms from collapsing. This is known as the Bohr model, and it's the one used in most textbooks. So to summarise, J.J. Thomson developed the plum pudding model with electrons held in a region of positive charge. Rutherford's alpha scattering experiment led to the nuclear model with the electrons orbiting the nucleus like planets around the sun, and Bohr refined the nuclear model by placing the electrons in shells or energy levels. But since the Bohr model, small adjustments have been made. In 1917, Rutherford discovered that the nucleus was made of protons. In 1932, James Chadwick discovered that it also contained neutrons. And in the 1960s, it was also discovered that neutrons and protons are actually made of even smaller particles called quarks. Oh, and atoms actually look a bit more like this, but we'll save that for another video. Thank you for watching. Please like and subscribe for more maths and science videos.
Have you ever seen an atom? Seeing as everything's made of them, you have, but have you ever seen one on its own? Over time, microscopes have become more and more powerful, allowing us to see deeper into the world of the ultra-small. Traditional light microscopes can be used to see things like these onion cells and the structures within them as they divide, pulling apart their chromosomes. But scientists have come up with a whole host of clever methods to observe far smaller things. Using beams of electrons instead of light, we can generate detailed images of chromosomes themselves. Recently, groups of scientists around the world are becoming able to see materials at the most fundamental scale, the atomic. One group from the University of California in Los Angeles have been getting up close and personal with nanoparticles of platinum, just a few nanometers across. Each of the tiny dots you can see here are actually individual platinum atoms. But researchers didn't stop at a two-dimensional picture. By imaging over 100 slices of the nanoparticle at different angles, then removing the noise with a special filter, they were able to map the location of almost every atom. The information was used to create a three-dimensional reconstruction of the whole particle in unprecedented detail. It may look blurry, but this particle is estimated to contain over 27,000 atoms, and so, like flies in a swarm, they appear to merge together. Every so often, though, we see the platinum's atomic structure align, granting us a moment of clarity. This technique is being used to analyze tiny irregularities in the structure of the particle called dislocations. Dislocations are subtle, like the misalignment of the green and red layers of atoms in this particle, but nonetheless they can significantly change the properties of materials, with effects ranging from a change in the efficiency of LEDs to the strength of metal alloys. Three-dimensional atomic scale imaging like this is bettering our understanding of the structure of materials on this truly fundamental scale.